This is working. Good. I've known Alfonso for many years. He's a great mathematician and a great friend. You're lucky to have him at Harvey Med. So, and he's influenced the lives of many of us in the room. You didn't mention John from Arizona, right? So,
Thank you.
yeah, so one of the people. Okay, so I'm going to talk about material science a little bit. So you have to pretend you're physicists or something like that, and think deep thoughts about physics. And these are my collaborators, Fengxin Chen, who Alfonso hired at UT San Antonio. He was my student. Shinfu Chen, who's at Pittsburgh. Adam Kamai, who's a postdoc with me and is in Poland now. He's Polish. Paul Fife, Utah. Xiaofeng Ren, who's at George Washington now, I think. Jinlong Han, and is in Utah. Shufeng Wang at Tulane, Guangyu Zhao at Cincinnati, Chunli Zhang, also in Utah. And I thank NSF for providing some support for this. So let's see, I've got some pictures here. So I've got this, some pictures of micrographs, so taken with a very powerful tools, electron microscopes, etc. So mu m are microns, micrometers, so a millionth of a meter, very, very tiny. And you see this very definite structure in a material. That happens to be aluminum, as they say in America, aluminium as they say in England, aluminium copper. So 67 to 33, there's the ratio. So it's an alloy, but the alloy separates into a couple of phases, a couple of concentration phases, with sharp kind of interfaces between at this scale. And let's see, I should make that a little bigger. And then here's another material. Copper nickel, where is it? There it is. You see dendrites, dendritic shapes. I don't know how you get rid of this thing. It's actually fairly pretty. It looks a little bit like snow. Now here, this is ND4SRTI5 something. It looks like a piece of cloth. Notice the scale on this. This is 4 nanometers. Okay, nano is smaller than micro, a thousandth. And that's what this is. That's 4. So there's 2. There's 1. Do you know how big atoms are? There's about 10 of them in a nanometer. So what you're seeing here are actually atoms. This is more or less the atomic level. Pretty good snapshot. But what's striking is the structure. Very ordered structure, very detailed. And it's not a homogeneous material, right? It's ND4SRTI stuff. I mean, it's an alloy, and you see there's some texture to the structure. So. And here's a colorful one, actually. This is poly-3-hydroxybutyrate, a polymer, and that's 1 micron. Yeah, so that's also a very small scale. You get these fantastic patterns forming in materials. So part of what I'm interested in is understanding why. Here's a couple more. So the first is a polymer, so long molecules that has a couple of different phases, well, there's quite a few components in the polymer, many different atoms, but the polymer behaves in such a way that it separates into different phases. These are different treatments. And it self-assembles into rather nice bands. The one below, the more colorful one, is actually an image-enhanced picture of NaCCOC. These people at Cornell made this. I just like the picture, but it's an actual material. The image has been enhanced, but you see there are sort of bumps in this material. It's not just two colors, but you see some shape. There are sharpish interfaces, but there is some shape to it, some diffusive kind of shape. So why do they form these shapes? What's going on here? Why do they support patterns? Well, I would say that they form patterns because of the interaction that the atoms have with one another. I don't know how to get rid of the sidebar, but anyway. So I'm going to model a material. So you're all material scientists right now. And we'll think of a material as a lattice of atoms. And each lattice point is one type of material. It could be all the same. It could be all the same, but maybe some spin up and some spin down, like a ferromagnetic material. Or it could be a mixed material, where some are one atom and some are another atom, a binary alloy. It could be that each one of the dots represents a small domain, and the color of the dot reflects some kind of average feature of the particles within that domain. So they may be at a little larger scale, still, the nanometer level maybe. So this is on average blue, and this is on average red. So I don't know who's winning that election. But the feature of this, the important feature, is that they are communicating one with another. Every dot is communicating with every other dot. It may be electrostatic forces, maybe magnetic, maybe gravity, it may be van der Waals forces, but they are all communicating one with another. And how they behave depends upon their neighbors. They're social or antisocial, depending, they may be ferromagnetic or anti-ferromagnetic. So they're communicating with each other at long range. Short range probably is more influential than long range. But that's the system. So I'm going to say the state of a material. We're going to use the term spin loosely. We're going to have two types, A and B, and little a of R is the occupancy of type A at position R. As I said, there may be little domains, and so you may have an average occupancy being a number between 0 and 1, any number between 0 and 1. Right, so it's not just on or off, or up or down, but on the average they are mainly up to a certain degree, and so on. The state of the material is the function A. So it describes the state at every lattice point R. And the century before last, we've got this statement by Van der Waals, who got the Nobel Prize, I guess, he says, we shall obtain, he was trying to understand how these materials behaved. We shall obtain a complete solution of the problem of understanding how they behave if we can express the free energy at each point as a function of the density, that's A, at that point, and of the differences of density in the neighboring phases, that's this long-range interaction, out to a distance limited by the range over which the molecular forces act. Okay, the range over which they act. Well, they act infinite range, but, you know, they become negligible the further you go away. Now, some materials act on a much longer range than others. Polymers have, they're big molecules and they act on a longer range than say, gaseous hydrogen. But we're looking at materials where the long-range interaction is more significant. So, but he talked about the free energy, so I have to tell you about the free energy. The free energy, or the Helmholtz free energy, I've got this automatic version. E is this difference. It's the total potential energy, H, of interaction, of all these pairwise interactions, minus the energy that you cannot use. The energy that you cannot use is due to entropy. T is temperature, and S is the entropy of mixing. Now the interaction energy, the potential interaction energy, let's see, can anyone see that red dot besides me? And I can only see it because I'm really close. I usually can't see these. Okay, the interaction energy of a field A is going to be this. So little a of R is type A at position R. Okay, the fraction of type A at position R. And this is the stuff at position R prime. So those are being multiplied together to represent the interaction of A's at R and A's at R prime. And then they'll be multiplied by a coefficient JAA, meaning we're interacting type A with type A, depending on the vector which goes from R to R prime. So it may depend only on the length of that vector, the distance, but it could also depend upon orientation. It could be an anisotropic interaction. I've done a double sum over the whole lattice, so I've got every pair R and R prime, but of course when I did a double sum, I counted everything twice, and so I got a 1/2. And I put a minus sign there to think, so I remind myself, if I'm talking about, say, a ferromagnetic material, and the capital J is positive, then they like to line up. So when they're the same, the energy should be low. Things go to low energy states. Okay, good is low, right? So the minus sign, if J is positive, is to reflect that. So that's type A with type A interaction, potential energy. Now if the occupancy is little a, occupancy of capital A is little a, then the occupancy of the other element, the other type, is 1 minus little a. So we've got 1 minus little a at position R, 1 minus little a at position R prime, that's B interacting with B, multiplied by a coefficient, JBB, R minus R prime. Don't worry, this is very boring right now, but we'll get over this. We're just going to get the equations. So there's B acting on B. And now here we have the A's interacting with the B's. The A's at R and the B's at R prime. And here we have the A's at R prime and the B's at R. And their coefficient is reflective of, you know, there's a subscript AB, superscript AB. Say we're interacting type A with type B there. And they could all be the same, but they could be different. All right, so now, one thing which is true If have an atom of type A over here and an atom of type A over here, and their interaction is such and such, if I switch their positions, the interaction will be the same. Okay? So the J, each of these J's will be symmetric in their argument. So J at R is the same as J of minus R. Okay, so they're symmetric. They're translation invariant. If I get this picture and I move it exactly the same over here, the interaction will be the same. So it's translation invariant, but as I said, it may be anisotropic. There may be some order. This may be happening on a substrate, and that substrate may be imposing some order. Or maybe there's some background magnetic field, or the way the stars are aligned, or something like that, which is providing some anisotropy. We're allowing that. It doesn't have to be there, but we're allowing it. Now, we don't like this mess. This is very complicated. And so what I'll do is I'll find all the pairs, A of R multiplied by A of R prime. Here's another one, and there'll be another one in here and another one in here. I'll collect all the A of R times A of R primes. I'll multiply and divide by 2. And then I'll say that's the middle term in the expansion of A of R minus A of R prime squared. There's actually a minus sign there as well, so that's handy. Of course, the J's are different, but I'll group those together. The JAA, JAB, and JBB, I'll group those together and call the result capital J. So if I do that, I'll get a capital J, I'll get a 1/4. Remember we had minus 1/2, but then we got to multiply and divide by 2 because we had A times A and we wanted 2A to get this perfect square. All right? And when I did that, there were all sorts of terms left over. So there was like an A of R prime. Here's an A of R prime multiplied by 1, multiplied by this JAB. And this was a double sum over R and R prime. This has an R prime in it, that has an R prime in it. But I could do one of the sums over R, because this only has the R in it. And the J is translation invariant, so I'll get some number if I do that. And I'll just get a single sum over R prime times a constant. And then there's another one I could do the other way around. And then there's some 1s here, and there's an A, and there's an A of R, and an A of R prime. I can do those as well. And then I've got some square terms, right? When I made this perfect square, I got A of R squared and an A of R prime squared, which I shouldn't have. So I group all those things together, and here they are. I've carefully arranged them in that way. And there's what the terms actually are. Okay, this is arithmetic. You do the arithmetic. Is there a reason I did that? That's more important. Well, yeah, there's a reason. This function h, actually this one, let me just point out that this d times summation of A of R, the d is the difference of interaction of J with BB, the interaction of B with B and A with A. If there was a symmetric interaction, like two minuses interacting in the same way as two positives, other way around, that's typically the case, then that would be 0. The other terms are actually symmetric about 1/2, the midpoint. Remember, A goes from 0 to 1. and if, these terms are symmetric about the midpoint. And that gives some asymmetry. Okay, so that's one reason I've written it in this way. It was symmetric before, you could say. On the other hand, If I wanted to minimize this whole thing, this top, and J were positive, I'd just make A constant. All right, that's sort of easy to do. Now I've got to get the free energy, so there's this second term. And people don't like to talk about entropy very much, especially if they're mathematicians. It's a physics term. But entropy is about, so here's the deal. You've got these atoms or spins, flipping up and down a lot. And when you raise the temperature, they jump around a lot more. And unless you are a Maxwell's demon, you can't extract that energy for work. You can't get anything out of that. How much is there? How much unusable energy is there? Okay, I said it depends upon temperature, but it also depends upon the possible rearrangements you can have. Right, you've got a bunch of spins going up, say. How many ways are there arranging that same number of spin-ups? Because they will all be visited. They will all be used. So here's how entropy is defined. If you've got A of R is the fraction of type A, and we're at a site little r, suppose that site little r is a patch, and there are actually n particles in that patch. Then little a times n are the number of type A's, right, because little a is the fraction between 0 and 1. These are the number of capital A's in that little patch at type R. The entropy is given this way. It's a probability. E to the n, S is the entropy, divided by Boltzmann's constant, this is Boltzmann's law, is equal to the number of ways of arranging those an particles in the n available positions. That's what the entropy of mixing is. So you've got this. Now you people are not algebraists, you're analysts. So if you're like me, you don't like factorials as much. You do algebra with factorials. So what do? We use Stirling's formula to change factorials to exponentials. So if you use Stirling's formula on this and solve for little s, and you take capital N to be fairly large, then the entropy at type A is minus k bracket A log A plus 1 minus A log 1 minus A. And then the total entropy is the sum over R of little a of S of A of R. It does get better. So now the free energy is this thing. The energy of a field A, H minus Ts, is the first thing that I showed you before, the J, R minus R prime, A of R minus A of R prime squared, plus the entropy. This is K times the entropy times the temperature, so we've got KT, A log A plus 1 minus A log 1 minus A, plus the other stuff that I mentioned. This is D A of R squared minus A of R plus little d A of R. Okay, there's the function. Function of a field. I've summed over all these lattice spaces, so if you give me a field, I will give you the free energy. That's what it is. Now, the nature likes to minimize the free energy. Okay? So now you're nature, and you get to minimize this function. Choose a state little a which minimizes that. And we'll divide the job up. Okay, so I'll take some of it. I'll do the top, and you do the other bit. I'll do the top, and I'm going to assume J is positive. All right, J is non-negative. So I'll minimize this by saying, take A to be constant. Any constant you like. right? Because that makes this 0, and 0 is the minimum it could be. So I've done my job, now you get to do your job. So you take a look at this function, and you spend some time mulling it over, and you say, well, what is this? Well, this one, we're more familiar with this. Here we have a quadratic. What kind of quadratic is this? We've got a minus d, a squared minus a. A minus a squared goes down with its maximum at 0. When I have minus a squared minus a, I just shift it over so its maximum is now at 1/2, but it's still going down. Okay? It's going down like this. And that moves it a little bit. What about this guy? What does a log a look like? Well, at 0 it is 0. That's good. But then as we go to a little bit positive a, what does it do? Yeah? It goes negative, right? Because log is negative infinity at 0. So a little bit away from 0, it's negative and big. And the a is positive. So that's negative. So we were at 0 and we came down. This guy does the same thing at 1, sort of in reverse. So it's 0 at 1 and then is negative just to this side. So it goes down. In fact, this guy is a smiley face. It's concave up. This guy is concave down. And they're added together. Which one wins? Depends on T. K is Boltzmann's constant. That's a constant. Don't mess with that. But T you can mess with. That's the temperature. So you increase the temperature and the smiley face wins. You decrease the temperature. Well, near 0 and 1, the smiley face still wins because you've got an infinite slope at 0 and at 1. But in the middle, around 1/2, the quadratic wins. I got a picture. I got a collection of pictures. So, how to make that bigger? Well, you can see. Okay, so here is where the temperature is bigger than some critical temperature. And then there's a critical temperature where they are just balanced, of concavity and convexity. And then below that critical temperature, the quadratic wins in the middle. But of course the logs win at the end, at the edges. So what we have is a constant state to minimize. Above critical temperature, you're in the middle. That's a perfect mixture of type A and type B. But as you decrease the temperature, you pass a critical temperature at which a phase transition occurs. There become two minimizers, one which is rich in A and one which is rich in B. Two phases minimize that total free energy. So now we're going to fix that temperature and have a material which supports two stable phases. And that's what I don't know. Am I on this page? Yeah. And that's what I was saying there. There is a critical temperature such that the stuff in the box, that's the hard one to minimize, is strictly convex. Okay, so we're fixing that temperature now, and we'll have two homogeneous states which minimize the free energy. And we're going to change variables and call the new variable u instead of a. So it's not an occupancy variable, but it's, some rescaled variable, so that the minima occur at plus or minus 1, because I may want to talk about plus or minus 1 rather than over there and over there. Okay, but it's the same picture. Okay, So there is the free energy. We have that double sum of j times u of r minus u of s squared plus a single sum over the lattice of the double well function. And we have rescaled. J may be anisotropic, but it is even. J of minus x is j of x. The two wells, if the little d was 0, the two wells would be at the same level, unless you put an external field in as well, and then they would be different. So in general, we'll take the wells to be not necessarily of equal depth. Okay, so we've got the double well potential. And by the way, we could, instead of taking this lattice structure and doing sums, we could continuize and do the same thing on the continuum, where in which case we get double integral and then a single integral. Okay, it's the same kind of structure. Okay, these are the things, these are the free energies that Van der Waals was talking about. Now, I've been talking about J being non-negative, but in fact there are materials where J actually changes sign. And in fact, when you try and push atoms too close together, they don't like that, and so they tend to act with a J of negative sign. Okay, so there's the free energy. I want to evolve my material. The pictures that I had at the beginning, of real materials, I want to produce those. Say we put all our materials in a pot and heat it up and stir it and then cool it down and see what kind of materials we get out. Well, so the material structure will evolve. And this is the principle I want to adopt. So that the material structure will evolve, that concentration field or that spin field will evolve in such a way to reduce the free energy as quickly as possible. So there'll be dissipation of energy somehow. The spatial function u is a function over states. So, over space and time. U is a state, depends on space and time. To evolve it according to the free energy, to decrease the free energy, suggests we do this. That we have our states U, each state has an energy. So if the floor is the family of possible states, then we've got an energy surface above every state. We've got an energy value, so we've got a surface. Now, if I've got a state over here and its energy is up there, and a state over there where the energy is lower, this state will move over to here so that the energy decreases. And will go in the way that most rapidly decreases the energy. So here's the first nonlinear functional analysis. U is a function of space and time. All right, we know partial derivatives functions, that's no problem. E is a functional. It takes a function and gives a number. How do you take the derivative of E? How do you take the gradient of this? This floor is an infinite dimensional space, function space. I've got to take this gradient. And we do it as we do it in vector calculus. We first get our understanding of directional derivatives, and we say, all right, if I want to take the derivative of E in the direction of V at position U, I'll add a bit of V, H times V, to U, take E there, and I'll take the derivative with respect to the incremental distance in the V direction, and evaluate at H equals 0. That's the definition. So the gradient of E at U is an operator that operates on another function v and produces a number. So that's a functional, a linear functional for each u that operates on v. We get to choose this angle bracket. That's a topology in the space of functions that we're dealing with. If we take square integrable functions, then the analysis is easiest. And this statement here, the star statement, becomes this. It turns out the gradient of that functional that I had, that page up, this guy, the gradient of this, if I take the derivative with respect to u, not with respect to x, with respect to u, the derivative incrementing u, you can see there's something like a convolution going on here. Well, that's what you get. You get what I've called NAC here, which means non-local Allen-Kahn equation. Allen and Kahn were material scientists, and they have a famous equation called the Allen-Kahn equation. This is the non-local version developed from these first principles. So u evolves with respect to time as the convolution of u with j minus number d, that same number we had before, which is the total integral of j, times u, minus f primed of u. F was that double well potential. It was like this. When you take the derivative of a double well potential, you get something like a cubic, which I don't know if it goes like that for you or the other way. But anyway, it's it goes up and down and up again. Okay, and d is this integral. So that's if you're dealing on all of Rn. If we were dealing with a bounded domain, then we just get the integral over the domain, and the convolution would be restricted integration to the domain. Okay, but if this was Rn, convolution means integral over Rn. If it were the discrete case, these would be summations. Okay, it's a discrete convolution. So there's the non-local Allen-Kahn equation, derived sort of from first principles. The hope is that this would predict the evolution of materials, provided we understand these coefficients j, these interaction coefficients. Okay, so now about Allen and Kahn. Here's how I can get the Allen-Kahn equation. So that first term in the free energy was this double integral, 1/4 double integral j, u of x minus u of x squared. And if you think to yourself, the interaction coefficient dies off rapidly with distance, you could say, well, this is going to give zero contribution when x is close to y, when x is far from y, zero contribution. When x is close to y, on the other hand, u of x minus u of y is close to the gradient of u at x dotted with x minus y. That's the mean value theorem. Right? That's the mean value theorem. So you get either 0 or something that looks like gradient squared times u of x times x minus y squared. If I take the x minus y squared and put it with the j and integrate once with respect to y, then I get like a j of y times y squared. That's a second moment of j. It actually turns out to be this, multiplied by a single integral of the gradient squared. So this part of the energy could be written this way, and the free energy functional would be this. And by the way, this is what van der Waals did, because it made it easier. And this is what Ginzburg and Landau did, because it made it easier. And so this is known as the Ginzburg-Landau functional. And now the L2 gradient flow is actually the Allen-Cahn equation, which is like a heat equation, ut equals Laplacian u, with a nonlinear source or sink term, which is that sort of cubic shape. And that's the famous Allen-Cahn equation with the no flux boundary conditions. So it's an approximation. This approximation is pretty good for a single function. But if you're saying for the entire functional, it's not a good approximation at all. What you've done is approximated bounded operator, that convolution operator, with an unbounded operator, namely the Laplacian. Well, unbounded operators are worse than bounded operators, so surely that's a worse equation. Well, not really. Cases, in some ways this is a lot better because we understand the heat equation quite well. This is a differential operator which we understand pretty well. And furthermore, solutions get smoother and smoother as time goes on. Well, they get smoother immediately. And there's some compactness that's going on. Okay, if I wanted to get fancy, instead of taking an L2 in a product, square integrable functions, I could have taken my function space to be the dual space of functions whose derivative is square integrable of mean value 0. Okay, this is, as I say, this is a little bit fancy, but there's a reason for doing that. If I did that, I would get conservation of species. So instead of having just a spin system, spins up and down, you know, like ferromagnets, which there's no conservation, they can just influence one another and they can change at will. If instead of that, I had my two species being species of atoms, so we've got so many atoms of gold and so many atoms of copper, you cannot say, oh, my neighbors are all gold, I want to be gold too, so I'll change to gold. You can't do that, right? You've got to have conservation of species. You can do that with spins up and down, right? Change your orientation, people do that. But you can't, you can't change copper to gold. So you have to conserve species. And if you do a conservation of species, then this is probably the best way to do it, to work in a different function space. And you get this non-local Cahn-Hilliard equation. So John Cahn is a material scientist, and Hilliard is another material scientist. They have a local Cahn-Hilliard equation. This is a non-local version. So we just have minus Laplacian in front of what I had before. We can also couple temperature into this system. So if I couple temperature, then so temperature, heat, is involved in the free energy. And it gets involved in this way. And then when you do an evolution, you get a system. So we have the same kind of non-local heat equation here, phase transition equation, where the phase transition is driven partly by the temperature over here. But then we also have the temperature changing. So theta t is Laplacian of theta. Okay, that's the heat equation. But wait, there's more. There's this L times U sub T. L is latent heat, U is phase. When the phase changes, there's a source or sink of temperature, of heat, right? Latent heat release or absorption. So this is a heat equation with latent heat of fusion taken into account, and then temperature drives the transition as well. So this coupled system also comes from this consideration. This is a gradient flow of this. But we could do other things which are a little bit different. We can also consider Newtonian dynamics. So if you consider Newtonian dynamics, so we've got all these atoms and they're at a certain position, they're being influenced by their neighbors, and that's a force, right? And force is mass times acceleration. The force is the gradient of the energy. So we could say acceleration is this minus gradient of the energy. And if you do that, then instead of the first time derivative here, you get a second time derivative, and this would be a non-local wave equation. So there's many things we can do. We can derive from this basic free energy consideration. So now some results. And there are by now quite a lot of results, both in the lattice and the continuum. But here we have this non-local Alencon equation. First, do there exist solutions, and are they varying continuously with respect to initial data and parameters, etc.? Are the solutions unique? Well, that's actually pretty easy for this. This is an ordinary differential equation in a function space. These operators, J star and this operator, these are bounded operators, and so actually you can use Picard iteration, or that fixed point technique, the contraction mapping theorem, to prove existence and uniqueness and continuous dependence of a solution to this, local existence anyway. Because of the shape of F, you can actually prove a priori bounds of solutions. Solutions don't blow up. So you can get global existence of solutions. That's fine. You can actually get solutions existing for a short time backwards in time as well, which doesn't happen for the heat equation. But this is an ODE in a Banach space. So you can get some backward existence if you should want it. And then there are many special solutions and properties of this equation. You can show that there are traveling waves, and I'll talk about that, and you can show that there are waves that fail to propagate. You can show that there are pulses and patterns, that there are crystal structures that are produced by these equations. So faceted pattern shapes. Okay, so I'm going to talk about traveling waves. The Alencon equation, that's the PDE, people studied that for many years. It has other names. The material scientists call it the Alencon equation. Biologists will call it something else, maybe. Anyway. So you look for a wave of propagation. We're going to change from one phase to another by sweeping across with a plane wave. So you look for a solution, u of xt, is u of x dot a is the direction that you're going to go, plus ct. C is the speed of the wave, where a here is a unit vector of direction. If you stick that in, but this is a function of one variable, call that z or something, u of z. Plug that into the Alencon equation, then you get this second order ODE. We like second order ODEs. We know everything about second order ODEs, more or less, don't we? Autonomous ones. So you can do some phase plane analysis, or you can do elliptic integrals, or you can do whatever you like. And you can show that this equation, so the pure phase is a plus or minus 1. I've said u of 0 equals 0 to nail it down because the wave can slide this way or this way. This is an autonomous equation. We're going from plus 1 to minus 1, or minus 1 to plus 1. And we'll just say it goes through 0 at 0. You can prove that there exists a unique solution that does that. A unique profile and speed. Okay, the non-local Alencon equation, on the other hand, is a little bit trickier. We'll convert it to a one-dimensional equation, just like we did here, by integrating in directions perpendicular to the direction of travel. So we'll call that new thing J tilde. and we'll take the integral of j tilde to be 1 instead of d. So the integral of j tilde is the full integral of j. So I've taken d to be 1. So it's j tilde star u minus cu prime minus f of u. F of u, oh, did I say what that is? Little f is capital F prime. Okay, same boundary conditions. Now this guy, how do I analyze that to find out if there's a solution? Well, if c is not 0, this is a differential equation of order 1, not second order. But c may be 0. I don't know what c is. C is one of the unknowns. So this may not even be a differential equation. And it's actually an infinite dimensional system. The other was a two-dimensional system. That was a two-dimensional phase plane. This is something happening in infinite dimensions. Phase plane analysis will not work. So I've got to use some more fancy stuff. So the idea is to do a homotopy. So here's some non-linear functional analysis again. We take the equation that we liked, look at lambda equaling 0, and it's the equation that we knew everything about. And we'll move lambda from 0 up to 1. 1 is the one that we want to know about. Keep the same boundary conditions. Define a function on our function space. Well, take that C2, right, because we've got two derivatives. Cross r, that's our unknown speed c, cross lambda into continuous by r. So this comma that. And we'll say, well, at lambda equals 0, we know there is a 0 of this, right? U of 0 equals 0, and this part equals 0. That we know that there is this wave. Call that U0, and speed C0. And now we're going to use the implicit function theorem. And the implicit function theorem, you remember, is this theorem. Whoops, not that. The implicit function theorem goes like this. Suppose I've got, these are my axes. Suppose I've got a solution to function equals 0, g u0, whatever. Function equals 0 here. I would like to now vary in this direction. Let's say this is the epsilon direction. And I would like to know that the function still has zeros nearby. Well, if the function is bowl-shaped, and has a unique minimum there, then there's no chance. What is there that causes this to perturb to have another 0? Well, one way to do it is say, if I walked in this direction, in this u direction, if this had a non-zero slope, say it's going down there, then the bit of surface represented by the function g must go clean through, and so must perturb, must have a curve of zeros, right? That's the implicit function theorem in a picture, right? And what was that? It had a non-zero derivative in the u direction. The implicit function theorem in infinite dimensions, which is how I have to apply it here, C2 is an infinite dimensional space cross R, that's one more dimension. I'll take a derivative of g in the infinite dimensional direction and want that to be non-zero. Okay. I want it to be non-zero. In other words, be an isomorphism. That's the technical way to say it. And that involves looking at this linear operator. This is the derivative of g at u0, c0, lambda equals 0. I want this to be an isomorphism. Actually, it's not quite, but with this tacked on, it makes it an isomorphism. It's to do with the first eigenvalue of this differential operator being algebraically simple, corresponding to translations. Nailing this down stops it translating. The implicit function theorem in infinite dimensional space is very handy and produces this result. This allows us to get off lambda equals 0 and move a little bit. Then, in the case that j is non-negative, we go to the end of our lambda interval. We do this perturbation. We've just moved lambda. This is lambda, actually. We've moved out to here. And we say, well, what happens there? Well, then we use some positive operator theory to show that the eigenvalue is, again, algebraically simple. And we can perturb it further. And we can keep perturbing it. Unfortunately, you can't get all the way to lambda equals 1. Because at lambda equals 1, you lose the second derivative, which is the space in which you're working. Things degenerate, and in fact, all sorts of things blow up. So you have to take a limit in a weak sense as lambda equals 1, and then do some regularity theory and monotonicity theory, and you get the existence of a solution, one of these traveling wave profiles. There are some surprises. The speed, usually when you have two different wells of different depths, everything slips down into the lower one. The wave propagates to the state with lowest energy. But in this case, the speed can be 0. You can get some pinning, some failure to propagate, either because of the lattice structure of or the long-range interaction. And in that case, the solution may be discontinuous. Let me not show those pictures. But corresponding to those sharp interfaces we saw in the micrographs. You can get these sharp interfaces that seem to stick there. For the wave equation, I'm out of time, but for the wave equation, we use a fixed point theorem. So this is a fancy fixed point theorem. It's actually a perturbation theorem for fixed points. Don't read the details. It's a fixed point theorem. The equation that we're dealing with is similar to the Klein-Gordon equation, which is this. It's a wave equation with a nonlinear term. This is diffusion instead of non-local diffusion. You can use phase plane analysis again to get traveling pulses, or you can write them down explicitly in terms of Sech functions for that. For the non-local wave equation, with very powerful interaction, which is short range, I can consider this. This term here is an approximation of a second derivative. You can sort of see that. Think of this as average of nearby neighbors minus the value in the middle, divided by the mesh size squared. Okay. Looks like, and so in some ways that's what it is. And there's a theorem, we do it for the discrete and for the non-local continuum version. We get the existence of a traveling pulse, which is close to that for the Klein-Gordon equation. I said we use the fixed point theorem, but here's the interesting thing. We go to Fourier transform space, get an equation. The Fourier transform of our proposed solution is some Fourier multiplier multiplied by the Fourier transform of a nonlinear function. Then we invert the Fourier transform, and we get u equals inverse Fourier transform of some nasty expression. C is the transform variable, convolved with the nonlinear function of u. This is a fixed point equation. It turns out that this middle bit in the limit in Fourier space, in the limit, this becomes the operator minus d c squared, which is a second derivative operator. But this is a differential operator being the limit of a Fourier integral operator. The fixed point theorem goes through, it applies, and we get the solution. So thank you.
We have time for one or two questions or comments. Anybody questions for Peter? Of course, we'll be here all day.
We can talk later.
Yeah.
First of all, thank you very much, Alfonso. It is really a great pleasure to be here again at Harvey Math. As